Software development security has been moved up the chain here, and it's a fourth domain, fourth most important. And the focus is definitely on that due to the fact that most of the errors these days is at the programming level, not so more anymore at the operating system, but at the domain. So software development security domain refers to the controls that are included within systems and application software and the steps used in their development. That is the system development lifecycle, the SDLC. Software refers to system software such as operating systems and application programs such as agents, applets, software, databases, data warehouses, and knowledge-based systems. These applications may be used in distributed or centralized environments. The candidate should fully understand the security and the controls of the system development process, the system's lifecycle, application controls, change controls, data warehousing, data mining, knowledge-based systems, programming interfaces, and concepts used to ensure the data and application integrity, security, and availability. We have to understand and apply security in the SDLC. That's our first step. We're going to look at some of the security controls, the effectiveness of software security. We're going to go through the software development and change management process. This is the whole SDLC, specialized security controls for database and web applications. We're going to look some at the malicious software such as viruses and worms and other threats in our development environment, and software engineering principles, which is quite important. Some programming concepts. Now, what I actually do from my side is actually looking at the software assurance maturity model. This is where we look at software development from a business function such as governance, the construction of the software, verification that things are done correctly, and finally the deployment in an environment. In the governance, from a security architecture point of view, we can look at the strategy and metrics. Metrics meaning we measure how effective we are. We can look at education and guidance, and also policy and compliance. In the construction, you'll see in the SDLC, we'll have threat assessment, we'll have security requirements definition, and then also a secure architecture. Then verification process is where we have assurance. We'll review our design, review the code, and also make sure that the testing is done and that the testing is documented. Then finally, in the deployment area, we have vulnerability management, environment hardening, and then operational enablement. The objective of the software assurance maturity model assists in the evaluation of an organization's existing software security practices. It allows us to build a balanced software security assurance program in well-defined iterations. It will demonstrate a concrete improvement to a security assurance program and also define and measure security-related activities throughout the organization. Our design consideration includes 3 steps here. An organization's behavior changes slowly over time. So it means that a successful software security program should be specified in small iterations that deliver tangible assurance gains while incrementally working towards long-term goals. It also states that there's no single recipe that works for all organizations. We need to understand that software security framework must be flexible and allow organizations to tailor their choices based on the risk tolerance and the way in which they build and use software. Also, guidance related to security activities must be prescriptive. All the steps in building and assessing an assurance program should be simple, well-defined, and measurable. This model also provides a roadmap templates for common types of organizations. The assumption is that the operating system is the source of security incidents and anomalies. The largest source these days for security incident is from applications, and specifically web applications. There's definitely a lack of version control. Ad hoc programming, meaning that people don't have formal security programming education. There's a lack of testing, and then security is not part of the development process. When we look at the type of programming languages, we've got generation 1, which was machine language. There you can see machine code, E3 equals a jump instruction. Then this was taken to generation 2 to make it easier for people to program, and assembly language was born. And assembly language is mnemonics to machine code. And that ASM, or assembly, or assembler, took all the machine code and created instruction based on the machine code. Then generation 3 to make it even more easier for people to program and to support a structured programming, which means functions and procedures. High-level languages were designed. Initially C with Kearney and Richard, and then other languages like C++ and Pascal and many more. The objective initially of C was a language that generated assembler code which was assembled. Generation 4, a very high-level language, more to the English language structure. We've got SQL, which is structured query language. We have other languages like DBase, Clarion, COBOL, and so forth. Generation 5 focuses mainly on artificial intelligence, such as Prolog, Lisp, Ops, and Mercury. There are many more languages. COBOL, we've seen. Fortran is another language. C, C#, C++. Interesting fact about C++, in the C language, if you want to increment a variable with 1, you'll say variable ++. So C++ indicates it should be better than C. We've got Smalltalk, Java, and Eiffel. Interesting fact here is that Smalltalk was the first commercially available object-oriented language with class as the main class. We have visual programming languages such as Visual Basic, Visual C, Delphi, Basic, Logo, JavaScript, and VB scripts. Now, visual programming languages once again make it easy and remove the complexity from the end product. Others definitely to mention is HTML or hypertext markup languages. We have HTML version 5, which we've seen in 2008 as a working draft, and then it's being pushed out currently. And we need to consider that it is a big step in the future, getting rid of things like Flash as we integrate it. However, although there's more control, we need to consider there will be more risks in the future. We've got XML, which is extended markup language. ActiveX is not a programming language, but an extension to the browser. So it's actually an OCX, a .ocx in the operating system, but it is actually a dynamic linked library. And it has to be mentioned because it actually has got direct access to the operating system itself. There's program utilities such as an assembler, which assembles the source code into object code. We have the compiler, which compiles the source code into object code. We have a linker that will link the object code with external libraries to create the executable. And then an interpreter uses pointer code to run a script. Examples of interpreted code is Perl, Python, PHP. And in Windows environment, we can see the WS script and also the PowerShell, which is pushed quite hardly. Now, when we look at programming concepts, we can look at a system model, which is a conceptual model that describes and represents a system. Von Neumann architecture is a bottleneck called the VN von Neumann bottleneck, which means that the instruction fetch and data operation does not happen at the same time. And object-oriented programming, we can actually look at inheritance, polymorphism, and polyinstantiation, which makes it easier for us humans to understand the way things work. When we look at distributed component object model, older technologies still used in some systems. We have CORBA, and also being pushed out for later technologies, Common Object Request Broker Architecture, and the later technologies used for programming between system communication and distributed programming is SOAP, which is Simple Object Access Protocol. It uses XML as a message protocol and sits at the application layer. Now, in object-oriented programming, we can look at data abstraction, which is a concept or idea not associated with any specific instance. Encapsulation is the information hiding mechanism. Messaging in OO, object-oriented programming, is a single means to pass a control to an object. If the object responds to the message, it has a method for that message. Modularity is the way we code to break things down into smaller modules. Polymorphism is the ability to create a variable, a functional object that has more than one form. And inheritance is a way to reuse code of existing object by inheriting functions, types, and attributes from a class. Now, when we look at information security governance, we just have to mention again a policy, which is management directive that establishes expectations and assigned roles and responsibilities. As we said earlier, it is a statement of intent. Standards, which are functional, specific, mandatory activities, action, and rules. A procedure is a step-by-step implementation instructions. Baseline is mandatory descriptions of how to implement security packages to ensure consistent security posture. And then guidelines, a general statement or framework or recommendations to augment or assist baselines and procedures. 4 enterprise architecture models we'll quickly look at. There's the Zachman, which although it self-describes as a framework, is actually more accurately defined as a taxonomy. TOGAF, which is also called a framework, which is actually more accurately defined as a process. We have the federal enterprise architecture, can be viewed as either an implemented enterprise architecture or a prescriptive methodology for creating enterprise architecture. Gartner can be best described as an enterprise architectural practice. Now, the next slides will show you a couple of these frameworks. Now, the first and foremost is the Zachman framework, which is a 2-dimensional framework with statements and intent. So we actually have the contextual items on the left-hand side, conceptual, logical, physical, and detailed. And then we can ask questions about each one of these right on top. Now, your objective to understand this framework is basically just take this framework and look at your enterprise and ask yourself those questions and see how this can fit into. We have TOGAF, which have a capability framework and also has the whole process where it is a cycle, where it learns from business operation and creates new business needs. We have the business vision and drivers and business capabilities. So the vision and drivers will go into the architecture capability framework and the architecture development method. So we'll go through that, get our guidelines for the development management method, and then we define our context framework. And finally, we can actually look at our enterprise continuum and tools. So as you can see, very prescriptive and quite a large item. I would actually suggest you go to the TOGAF, which is an open group forum, and actually look at that and download it for your benefit. Many organizations are looking at TOGAF to implement the architecture framework. We have the Federal Enterprise Architecture Framework from the Federated Systems in the United States, and Department of Defense looks at this. It looks at your business-driven approach, component-based architecture from a top-down model. We have performance reference model. We have inputs and outputs and outcomes and performance indicators. Then the business reference model, we look at lines of business, agencies, how do we work with customers and partners. A service component reference model, which looks at the domains, the types, and my service components. Then at a lower level, we have a data reference model, where it's business focused on data standardization, cross-agency information exchanges. How do I get my data and how do I give my data? And then finally, right at the bottom level, at the lower level, we have technical reference model, which is my services, components, interfaces, interoperabilities, and looking at technologies and recommendations. And the final one is the Gartner Enterprise Framework. The nice thing I like about this one is that we look at our architecture, we look at the way to get there, such as develop requirements, my principles and my models, and then I'll look at my gap and I'll actually go and do a cycle of documenting this, look at the architecture and closing the gap. 4 models of approaching this. Other models that you can look at is the Coben Governance Framework, and we did see that in the risk management side. Now, control objectives for information and related technology. COBIT is an IT governance framework created by Information System Audit and Control Association, ISACA. Now, COBIT controls can encompass other issues such as NIST SP 800-53. We've got other ISO and IEC standards such as 17799, which is now the 27000 series, and an IT process management framework such as ITIL, capability maturity model, and also service management. And the project management is also considered here. Now, COBIT governance strategic alignments looks at value delivery, resource management, risk management, and performance measurement, removing the compliance requirement from a governance point of view away from management. And so we can separate those two. We've got the ISO 15288, which is a systems lifecycle process. And what this encompasses is system software engineering process. That's my technical processes. We've got project management processes, project support infrastructure, organizational project enabling processes, and then contract business management process such as agreement processes. That's my service level agreements, as you can see from my software engineering, project management, and SLAs. The software capability maturity has got a few levels. It's got 5 levels, first being initial, whereby the software development process is characterized as ad hoc. Success depends on the individual effort and heroics. Level 2 is repeatable. This is basic project management, processes that are established to track performance, cost, and scheduling. We have level 3, which is defined. It's tailored software engineering and development processes that are documented and used across organizations. Level 4 is managed. This is where detailed measures of product and process improvement are quantitatively controlled. And level 5 finally is optimizing, which continuous process improvement is institutionalized. What I often find is a lot of companies are sitting at level 2. They want to get to level 4, and it's very easy then to define the gap and actually tell them how to get there. Now, a little bit more on the software engineering capability maturity model. You look at this, where it's not performed right up to continuously improving. We have performed informally level 1, planned and tracked, well-defined level 3, qualitatively controlled, and level 4, and finally at the last model is continuously improving. Now, you can look at this and actually look at your organization, and for the benefit of the exam coming up, look at and see if you can actually identify in your environment what the differences are. Now, also, when we look at from a security-based practices, we've got 11 process areas. And also, from the software engineering point of view, from a security software engineering, we've got project and organizational-based practices, also 11 process areas to worry about. So if you look at security-based practices, we administer security controls, we can assess the impact, we can assess security risks, assess the threat, assess the vulnerability, build an assurance argument, coordinate security, monitor the security posture, provide security input, specify security needs, and finally verify and validate my security. This is my base practices. Then when I look at my project and organizational base practices, we can ensure our quality, we can manage the configuration, we can manage project risks, we can monitor and control technical effort, we can plan technical effort, we define an organization's security engineering process, we improve the organization's security engineering process, we manage product line evolution, manage security engineering support environment, provide ongoing skills and knowledge, and then finally, we will coordinate this with suppliers. Now, when we look at system or the software lifecycle security, there's a couple of models we can look at. There are project-based management-based methodologies. We can look at models and processes such as the waterfall, which we have the waterfall and also the modified waterfall model. We've got the spiral model, and also in the RAD and JAD, or rapid application development and joint application development, in the iterative development models. The SDLC process has been defined clearly inside the ISO 12207 and also the 15288. And when we look at the initial waterfall model, it gives us 7 steps there. We've got requirement specification that is usually sitting with the user, and do the URS or the user requirement specifications. We'll then design the solution in step 2. Step 3, we'll do the construction, or otherwise known as the coding. Integration is step 4. Step 5 is testing and debugging, which is validation. Step 6 is installation, and then finally is the maintenance process. Now, the waterfall model is a one-step approach trying to get something out. Now, when it's a large project, we have to look at the spiral model, which will look at a waterfall model, but actually can go back in time or back into the cycle and actually develop my concepts, my requirement plan, my verification, validation, do a prototype, second prototype, do the operational prototype, and get that out. And as you can see, we can get the objectives, identify and resolve our risks in step 2, develop and test in step 3, and step 4 we'll go and plan the next iteration. Now, the iterative or incremental model has got phases. It's got the inception, which identifies the project scope, requirements, functional, non-functional, and risk at a high level, but in enough detail that work can be estimated. elaboration delivers a working architecture that mitigates the top risks and fulfill the non-functional requirements. Then the construction phase incrementally fills in the architecture with production-ready code produced from analysis, design, implementation, and testing of the functional requirements. The transition delivers the system into a production environment. This is just a very good explanation of visually what the iterative or incremental model defines. We have got the 4 phases, which is the inception, elaboration, construction, and transition phases. And each one of these have got sub-phases. And then we have our business modeling, a requirements definition, analysis and design. And as you can see from that slide and that image, where each of these focus on predominantly. Now, rapid application development has also 4 phases. It's got the requirements planning phase, a user design phase, a construction phase, and a cut-over phase. Now, to go through a little bit of the theory, the requirements planning phase consists of the following. It will combine the elements of the system planning and system phases of the system development lifecycle. The users, managers, and IT staff members discuss and agree on business needs, project scopes, constraints, and system requirements. It ends up when the team agrees on the key issues and obtain management authorization to continue. In the user design phase, during this phase, the users interact with systems analysts and develop models and prototypes that represent all system processes, my inputs and my outputs. The rapid application development groups or subgroups typically use a combination of joint application development, such as JAD techniques and other case tools, to translate the user needs into working models. And CASE stands for Computer Assisted Software Engineering. The user design is a continuous interactive process that allows users to understand, modify, and eventually approve a working model of the system that meets its needs. In the next phase, the construction phase, it will focus on program and application development tasks similar to the SDLC. In RAD, however, users continue to participate and can still suggest changes or improvements as actual screens and reports are developed. Its tasks are programming and application development, coding, unit integration, and system testings. And then finally, at the cutover phase, which resembles the final task in the SDLC implementation phase, including data conversion, testing, change over to a new system, and user training. Compared with traditional methods, the entire process is compressed. As a result, the new system is built, delivered, and placed in operation much sooner. Its tasks are data conversion, full-scale testing, system changeover, and finally user training. Now, Agile software development is a group of software development methods based on iterative and incremental development, where requirements and solution evolve through collaboration between self-organizing, cross-functional teams. It promotes adaptive planning, evolutionary development and delivery, a time-boxed iterative approach, and encourages rapid and flexible response to change. It is a conceptual framework that promotes foreseen interaction throughout the development cycle. This is a very good example of the Agile development stages. As you can see, we starting and do a continuous process. We have daily acceptance testing, stand-up meetings, and development. This is a development that many companies take up due to the fact that you can deliver very quickly and manage it adequately. Sometimes you have multiple meetings during a day to get the software out. Now, the extreme programming actually is the predecessor to Agile, because as you can see here, we have planning and feedback loops, which can be minutes, hours, and days, much quicker than most software development environments. Now, there are software development methods. We have iterative development we've seen. We've seen JAD, such as a joint analysis development. We have prototyping to get the things out with the user. We have modified prototyping model using case tools to get things out with the user. We've got an exploratory model and then also rapid application development. Now, JAD can also be joint application development. The SDLC phases is quite important to look at these initially 5 phases. There is a 6th phase, which I don't identify here. However, we see it critical from a security point of view because it's a decommissioning phase. My first step is project initialization and planning. We have the functional design specification in step 2. Step 3, we've got the detailed design specification. Step 4, we have to develop and document. And finally, in step 5, we acceptance testing and transition to production. Now, each part of the system development lifecycle, let's look at the actual phases. Phase 1, we've got project initialization and planning. As you can see there, we have to, from a development point of view, we have to establish user requirement. From a security point of view, we have to determine our security requirements. We have to identify alternatives from a business point of view, and security will conduct a risk analysis. Business will select and approve. Security will define a security strategy based on the selection or the improvement of software. The functional design specification, business develops a project plan, that's the developers. Security identifies security areas. Business will identify functional requirements. Security will establish security requirements, prepare a risk analysis and contingency plan here. Business will set a test strategy, and we will define from a security point of view all the tests that we have to do. Business will define a strategy, and we will, in line with business, include security requirements in the RFP and the contracts. The developers will develop a functional baseline, and from a security point of view, we will include functional security requirements as part of their development. In a detailed design specification, developers prepare a detailed design. We'll have to ensure that they'll establish a security specification based on the minimum guidelines and minimum baselines. Developers will update testing and goals and plans, and we will align with them from a security point of view and update our security test plans. Developers define a formal baseline, and this is where we will document our security baseline. And the security baseline, we get the documentation from the company standards. The system lifecycle, when we develop and document, developers will develop the system. We will develop the security code or consult to the developers on developing the security code. Then the unit testing and evaluation will take place, where the security will be tested to make sure that the assurance is adequate. They will document the system, and we will document the security code. In the acceptance testing, the final phase from a system lifecycle, the acceptance testing and transition to production, the system components will be tested. The security components along with the system components will be tested. Security in an integrated system will be validated according to system performance. Integrated systems will be implemented along with the security code. We will document the security controls for the project manuals and certify that the secure operation is working as designed for the acceptance phase. And then at sign-off, at the acceptance of the system, the secure systems will be documented and accepted. Finally, as part of the security, a decommission or disposal, it will require that critical data is recovered and destroyed, media sanitized and destroyed, and the software is removed. When we look at software protection, there are a couple of things that we've seen initially in the main one, which is the reference monitor for access control. The reference monitor is a conceptual abstraction of a machine, system, or software that mediates access of objects by subject. A trusted computing base is a system of security controls that meets the confidentiality and integrity of security objectives. A secure kernel is a trusted computing base that implements a reference monitor concept. Now, when we look at the reference monitor, it is performed by a reference validation mechanism. The reference validation mechanism is a system composed of hardware and software, and in the operating principle, it has that the reference validation mechanism must be tamper-proof. The reference validation mechanism must always be invoked, and the reference validation mechanism must be small enough to be subjective to analysis and tests to assure that it is correct. Now, when we look at operating system, it shall be evaluated at CISSP B2, that is structured protection and above. And as you know, from level B, we have labeling. A trusted computing base is the totality of the protection mechanisms within a computing system: hardware, firmware, software, processes, and transports. Also, the TCB maintains the confidentiality integrity of each domain and monitors 4 basic functions: process activation, execution, domain switching. This is from user system mode, memory protection, and all input and output operations. A secure kernel is an implementation of a reference monitoring mechanism responsible for enforcing the security policy. It meets the following 3 conditions: completeness. All accesses to information must go through the kernel. Isolation. The kernel itself must be protected from any type of unauthorized access. And verifiability, which means the kernel must be proven to meet design specification. Processor privilege states protect the processor activities that it performs. Privilege levels are called rings, and for example, in the Intel x86, it has 4 privilege ring levels. Ring 0 contains the kernel, functions of the operating system. Ring 1 contains the operating system, such as device drivers and the hardware abstraction layer. Ring 2 contains the operating system utilities, and Ring 3 contains user applications. When we look at ring protection in virtual machines, VMware ESX moves the hypervisor to Ring 0. Now the guest operating system and operating system now moves to Ring 3, the utilities to Ring 2, and the applications at Ring 3. And when we look at the product specific like VMware vSphere, further abstracts the hardware layer, or the hardware abstraction layer HAL, where the virtual machine file system, VMFS for abstraction of data storage. It also has VDS for abstraction of the network layer, and vMotion for distribution and processing power to high availability. Now, this is not product specific, but you need to understand that virtualization is a huge issue in the future from a security point of view. Additional software protection mechanisms include things like cryptography, specialized access control, open source, so that end users can review the source code, social engineering awareness, backup and redundancy controls, malicious code control, documentation and common program controls. We've got mobile code controls, data contamination controls from a programming point of view. We've got sandbox such as a Java virtual machine. And then finally, refocus on access control, as this is the primary consideration when we go into a system. When we look at threats and malware, buffer overflow occurs when a program or process tries to store more data in a buffer, and a buffer is a temporary data storage areas, than it was intended to hold or allocated. The vulnerability is caused by a lack of parameter checking and or enforcement for accuracy and or consistency by the software application or operating system. To make sure that we protect against the buffer overflow, we can actually do practices of good system development lifecycle, code inspection and walkthrough. We have programmer implementation, parameter checks, and enforced data rules. We can apply patches for operating system and applications. If available, implement hardware states and controls for memory protection and buffer management for operating systems. Memory protection is the enforcement of access control and privilege level to prevent unauthorized access to operating system memory. We can ensure to make sure that we protected that all system-wide data structures and memory pools used by the kernel mode system components can only be accessed while in kernel mode. Separate software processes to protect private addresses space from each other processes. We can have hardware-controlled memory protection, and this is built into the CPU. Use access controllers to protect shared memory objects. A covert channel is an uncontrolled information flow or unauthorized information transfer through hidden communication paths. We can have a storage channel and a timing channel. A storage channel can mean something like somebody changes a timestamp in a file to indicate to another person when to transfer money illegally. Timing channel could be a password changed on a Friday and a user only uses it on a Monday, but in that time period between the Friday and the Monday, if it's a default password that an organization uses, a hacker can use it with that knowledge. Now, how do we protect against covert channels? It says that we have to identify potential covert channels. We have to verify and validate the existence of that covert channel, and then finally close the covert channel by installing a patch or packet filtering security mechanisms. Cryptography provides confidentiality, integrity, and authentication and non-repudiation information operations. We've seen that in domain 5. Asymmetric key cryptography, because of slow cipher operation speed, is mostly used for key management functions. Symmetric, because of the speed, symmetric key crypto systems are used for crypto operations. For example, SSL or TSL at the transport level, communication paths, email and SOAP messages at the message level, or otherwise known as at the application level. We also have hash functions such as message digest, message authentication code, and key hashed message authentication code, and then finally digital signatures. Password structures, we need to look at and consider password lengths, the complexity of passwords that have been used, such as upper, lowercase, letters, numbers, and special characters, not using any common words found in the dictionary. Then password maintenance, there can be different standards, such as password change in how many days, for example, every 90 days. Passwords can be used with intent password changes, or allow only one change every 24 hours. Password files must be encrypted and access controlled. Now, all the passwords I mentioned here, it is a very difficult thing to maintain and control, and passwords for future risk is high. The granularity of controls means the fineness of the control. How fine can we control a system? There's definitely issues to consider, such as separation of duties, which means that the process is designed so that separate steps must be performed by different people. It will force collusion if any fraud needs to take place. It defines elements of a process or work function and divides those elements among different functions. And that leads to separation of duties. Least privilege is a policy that limits both the system's user and processes to access only those resources necessary to perform assigned functions. It limits users and system processes to access only resources necessary to perform assigned functions. Also, then the separation of duty. Of separation of system environments, we must make sure that the development, the test, and the production data is definitely separate and segregated. Other security control includes the risk of social engineering. We can worry about security awareness training, backup, malicious code, malware, virus protection controls. We can install antivirus software, host intrusion detection system. We can enable access control to critical system files, can ensure that backups are done, not only the backups, but the recovery is tested, and we can encrypt sensitive information for confidentiality and integrity. Mobile code controls, we can install a sandbox for access to control of mobile codes. An example is Java containers or Java virtual machine, where the Java applet's running in a web browser. The applications using the Java remote method invocation RMI to run the Java beans. We have discretionary access control types. We've seen that in domain 1, access control, where the information owner determines who has access and what privileges do they have. Mandatory access control, where information and classification and system determine the access. Access decision is based on the privilege or the clearance of the subject and sensitivity or the classification of the object file. Requires labeling or data tag as known. Access control or capability matrix, which implements through the use of access control lists. And then view-based access controls, authorization of specific view by tables, columns, and key sets. A virus, which we all know is a big problem in a management of an IT environment, is that it likes to reproduce. It requires some action by the user and may have payloads, which means bad code it can execute. Payload will take a while to activate in order to replicate. It needs a host. You have different types of viruses. You've got file infectors, boot infectors, system infectors such as rootkits. You have email viruses, multipartite viruses that actually tries to hide it using different techniques, macro viruses, scripts, and then also hoax. Hoax is a virus because it is spread by people, a host, and it also wastes system resources. Then we have techniques that viruses use for anti-detection. It can act in stealth mode so that it hides itself from antivirus software, tunneling through other systems, using other software and ports to go through. Polymorphism, which means it will change its signature or use the encryption and change the key often so it cannot be detected by signatures, scanning antivirus software, and then antivirus disabling. So viruses can also disable your antivirus, And what I usually suggest is to go to a website called Virus Total, which you can upload a file and that it will push it through all the known updated scan engines, virus scan engines, and give you results. The objective of a worm is to reproduce, nothing more. However, it uses loopholes in a system, and although it says often attacks the server software, it will use those weaknesses and overload the server environment, such as your mail server. A Trojan horse is an application purported to be a positive utility, however, has got hidden negative payload. It is used often in social engineering to obtain information for further attacks. Examples I've seen is Whack-A-Mole, which, if you ever played it, you were infected with a NetBus Trojan. And there's also that you can wrap your own Trojan applications using applications such as Silkwrap and Ninja. Although it's not recommended to do that, but it's part of the training to understand that there are these risks. However, those will be detected by antivirus software. A logic bomb is generally implanted by an insider, waits for a condition to be met, and triggers a negative payload. For example, if I'm a user sitting, working for your organization, and I'm worried to be fired, got rid of, and I've got access to the HR database, I will write an application to look at my status as an employed employee. And once I'm actually not there anymore as an employed status, I will trigger a negative payload such as deleting files or databases. Diddlers, backdoors, and rats. We have data diddlers, which can modify data randomly and also affect your backups. Backdoor or trapdoor is something that's hard-coded inside the system to allow programmers or other people to get access without going through system maintenance, the formal procedures. And then remote access Trojan is applications such as BackRFS, which was developed to get access to your system. Although now it's called as a remote access support utility, high-risk Trojan at the end of the day. Another threat is distributed denial of service attacks, zombies sitting on a server. Pranks are definitely a threat because they will again waste time and can confuse users. Spyware and adware gets information from your system, so it's information disclosure. Phishing, farming is an attack using email, and also whaling. The difference between phishing and farming and whaling is that it is more directed. At the end of the day, farming and whaling is directed to users and not generally. And botnets are actual network infections, machines infected on a network worldwide that users can control, and these botnets can be sold to perform a denial of service attack. Now, when we look at audit and insurance mechanisms, we need to ensure that information integrity is allowed. There are things like hash functions such as MD5 or SHA-1. If you download files, applications from the internet, there's usually a hash function that you can verify that it hasn't been tampered with. Also, from an information auditing, from a risk management point of view, they can look at it. And some companies try to sell assurance on malware, meaning that if you actually take out a policy, you get attacked by a virus, they will actually make sure that it is restituted to the original function, or they pay you out. Testing is the last chance to avoid a disaster. The problem with testing, though, is that although it's intended to find problems, it should push it to the most capacious augment, meaning that it should test more than you expect to be online, for example. You must not compromise privacy with test data, meaning that you mustn't take production data and move it into a test environment to test your data. In configuration management, it is important to document all changes of system application, updates, patches, and patch management. We need to understand also what to patch and definitely make sure that the critical patches are deployed as soon as possible. The problem is that if we patch, we may break some systems, and sometimes it's not possible to revert back to the original one or have a backup procedure. So what we can do is looking at the patch management process and use virtual machines to test those and take snapshots. And in a virtual environment, we can revert back and have a proper backup procedure by just taking a step back on the actual snapshot. There's definitely areas where we can look at different types of distribution systems for patches. We can have push or pull. Push meaning that from a central point we'll push it to workstations, and in a pull, the workstation will push it from a central environment. The problem with the push technology on a network where you have huge latency is that the patches may fail, or that machines may in a remote area be off. Patch failures, and sometimes it says that it has successfully completed, but it hasn't gone and requires a reboot. There's definitely inadequate testing and validation sometimes in organizations. It's a high risk. A patch rollback, if a system is running in production mode and not in a VM environment, patch rollback may be problematic. The load on the network will be a problem, and also stability issues with other regression issues, meaning that another system that I've tested, if I successfully tested my patch management, but I'm deploying into a system which is slightly different, I may have stability issues. Now, when we look at databases and database warehousing environment, it is important to understand that database management systems was developed to manage information from many sources in one location. It does eliminate the duplication of information. This is called normalization of information. It preserves storage space. It prevents inconsistency in data by making changes in one central location. That is a data dictionary. A database environment is organized a collection of data, and a database management system should provide a transaction persistence, fault tolerance and recovery, sharing by multiple users, and also security controls. The first model we look at is a hierarchical database management system where it stores records in a single table. There could be a parent-child relationship, but it's limited to a single tree, and it's very difficult to link those branches. Then, at the network step, at a network database management system, representation of data as networks of records and sets that are related to each other, forming a network of links. Record types can be records of the same type, and set types can be a relationship between record types. Now, when we look at this database model, we can actually see there's a user interface, there can be an application program, and then the data administrator that will actually change the data definition interface. A user will run an application that will have end-user queries, and the application will also be part of the application processes, such as possibly stored procedures or business rules. The database management system will allow access to data access and some control logic. Physical data and also the schema. The schema is the definition of how the database looks like, and that will be done through the administrator. A relational database is the most frequently used database model at the moment. Data is structured into tables, columns represent the variables or the attributes, and rows contains the specific instances or records of that data. In this example, we have the author number here. This is my primary key. A primary key is a key that cannot be duplicated, and those are my actual tuples or rows and my attributes. And then when we look at a parent-child relationship, here is a foreign key, which is a reference to my primary key. The reason why I actually have a foreign key is that I can create cascading updates and deletes on actual records. For example, if I have here a primary key 234567 and my foreign key, which can contain duplicates, meaning that this author could have written many books and they have a relationship. So if I delete this one, I may want to delete all the references of the books in my child table. So deleting that one will actually make sure that everything is deleted in this table. Update cascade means that if I change this to an 8, everything will be referenced and changed to an 8. I will not lose that reference. That means referential integrity. Now, relational database security issues includes systems like ensuring that the integrity of the input data. That can be from a front end, preventing deadlocking, meaning that if two users sometimes require access of the same record, code may be written in such a way that both don't get access, but they are locked in the process. And then also what we need to look at is access controls. Where do we put this? Is this at the end user, at the application level, or backend at the database level? To communicate to databases, there are interface languages, also known as middleware. Open Database Connectivity, ODBC, JVDBC, XML, and SQL, Structured Query Language. Now, XML is Extensible Markup Language. Although it's not directly used to communicate to the system, it is a subset of other protocols. New protocol being in the market these days is JSON, which uses XML to communicate to databases over the internet. The objective of this interfaces or middleware is to hide the complexity of the programming interfaces required by the end users. Database security issues include such as inference, aggregation, which means that I can obtain information referring to a database and I'm not allowed to know. For example, if I'm a capture clerk at a medical suite and I get the forms from the doctor and the doctor says that this patient has got a sickness of code 46. Now, I'm not supposed to know that what 46 means, which protects the patient's privacy. However, if I actually get information from another source of what that means, that is aggregation. There's also issues like unauthorized access, improper modification of data, access availability can be a denial of service, query attacks such as SQL inject, which is the most common attack at the moment, bypass attacks using parameter checks, interception of data on the wire, I can sniff, web security, and also data contamination. Now, a view-based access control is a limited control or constrained view where sensitive data is hidden from unauthorized users. The controls are located in the front-end application or the user interface. Now, from an SQL point of view, this is the command that you can create a view. For example, create view with a view name as then the SQL command, select column names from table name where the condition should be met. And the condition could be where user Joe is the manager. So we can get all the staff and their salaries where it's related to his or her manager. A data warehouse is a consolidated view of enterprise data. What do we need to do? We create a data mart. The data mart stores a subset of data from a warehouse. It is used for business intelligence or reporting and analysis. This is designed to support decision-making through data mining. Now, how do we build a data warehouse? We're going to feed all the data of the organization into a large, high-security database. We're going to normalize the data. We're going to mine the data for correlations to produce metadata, and we're going to sanitize and export the metadata to its intended users. Now, when we look at metadata, it is information about data, such as otherwise known as data about data. This provides unseen relationship between data. There are two types of metadata you need to consider. There is structural metadata, which is about the design and specification of data structures, and it's more properly called data about containers of data. And then descriptive metadata is about the individual instances of application data, the data content. Now, knowledge discovery in databases, or KDD, is part of artificial intelligence. It is methods for identifying patterns in data. Some knowledge discovery databases methods use artificial intelligence techniques such as probabilistic models and also the statistical approach. It can do a classification approach of the data, deviation and trend analysis on the data, doing neural networks of correlations between the nodes, and then also an expert system approach which will have rules to be evaluated. Now, when we have a knowledge management security systems, we need to protect that knowledge of the database. That is usually, sometimes for some organizations, the actual asset of the organization. Routinely verified the decisions, meaning that if my knowledge management system can learn itself through time due to the fact that it actually gets more rules, we can have a verification routine that we always will submit and make sure that it is working as designed. So we know the answer, we'll put the question in, and if the answer is correct, we're happy that it is working as designed. Also, online transaction processing, OLTP, is a recording of transaction as occur in real time. Need to consider, a couple of years ago, most of the transactions were done in batch when the system was able to do it. The security concerns are concurrency and atomicity. There are lock controls that we have to worry about, and also an ATM or automatic teller machine for a bank is an example of a commercial transaction processing application. When we look at databases, the lock controls, also known as the acid test, most database vendors try to make sure that this is met. Atomicity means all or nothing, so you either do it or not. Not anything partial will take place. Consistency, there's valid states in the access to the data, for example, read access, read write, or edit mode. Isolation, it means it doesn't interfere with anything else in the databases, so it's by itself. And durability, it will continue, meaning that if I switch the database off, and then on, and it failed during a time, it will carry on as designed. In a web application environment, we need to consider things like vandalism. We'll have hackers out there that would like to deface a web page. Now, when they do that, that's quite easy. Then you fix it. The problem is that if you have financial fraud or privileged access or continuous privileged access of a hacker on the back end and you don't know about it, that is higher risk than actual vandalism that you can see the changes. There can be theft of transaction information, intellectual property, and then also denial of service. The majority of the hacks is at the application level. Firewalls provide minimal protection because say, for example, open port 80, and at port 80, it is the application level, and that's where the hacks take place. We can also consider that information gathering is an objective of a hacker. Administrative interfaces are left there when we install it. This has to be removed. Sometimes configuration management is not adequately done, and the system is left with, for example, the FTP server anonymous on read-write. Also, from an authentication and access control point of view, we need to monitor and log those. Input validation and parameter manipulation, we need to do validation of those parameters and also input to make sure that only the data that needs to come through is verified and correct. And also session management. One thing we can monitor to actually look at, suddenly we've got normally 100 connections on the web server and suddenly 100,000 connection. Those could be indicating a possible hack of the backend and users abusing that. SQL injection is the most common problem in web application interfaces these days. SQL injection occurs when an application sends an untrusted data to an interpreter as part of the command or query. These untrusted data can be SQL queries, LDAP queries, cross-path queries, etc., which means an attacker can alter the logic of the SQL query to bypass the security. For example, authentication and authorization to gain unauthorized access to data, for example, steal, corrupt, or change the data. It tricks the interpreter to execute unintended commands. And this is how LinkedIn passwords were compromised, and also Yahoo email user IDs and passwords. When you look at web applications, we need to make sure that we validate all input and output. Fail secure or fail safe, meaning that when it fails over, it does no harm and people don't have access to the data as designed. Make it simple, because complexity is the enemy of security. Defense in depth, meaning we have to look at all the paths. You are only as secure as your weakest link. And the problem with security by obscurity is that if we think people don't know how we've designed it inside, it can leak out. So what can we do about that? We can make sure we don't cache any secure pages, even secure fields such as your banking details when you log into your bank. Ensure all encryption meets industry standards. You'll see that in Domain 5 cryptography. Monitor third-party code for vendors for security alerts. This is part of your incident management program. Handle exceptions properly, meaning don't give too much information out to the end user. Do not trust any data from a client. Do not trust data from other service partners or other parts of the applications. You need to make sure it goes through a sanitation process. So basically, in this domain, we looked at software-based security controls. We understand the software development and change management processes for web-based applications and also databases. We had a look at malicious software and also some engineering processes.